Welcome to fifth lecture of course on data-enabled tribological engineering from experiments to predictive models. The topic of this lecture is wear measurement technique. First question comes, we have been dealing with the tribology, then why we are especially using the word wear measurement? Why not a tribological characterization as such? Yeah, it's correct. We measure also friction losses, but more weightage is given to the wear, reason being change in a wear is much more significant, many more times compared to the friction. So that's why we give more emphasis on wear measurement, and we keep friction, we measure the friction also, but more weightage is given on a wear measurement for our purpose. So let's start. We say the wear test to simulate practical conditions. The first thing is that why do we really require a wear test? Is there any reason? Yeah, there are a number of reasons. We say that we need to really come up with the newer materials which are very good, particularly for tribological situations. So new material, whenever we invent or really come up, they need to be tested in a real world scenario. But testing in real world scenario will become a very costly. So we want to reduce the cost. So initially we want to test against only 3 parameter or 4 parameters. Once that we are happy with that, then we go for the more number of parameters and we go for the real scenario. And then what we see when we do this one, we can also go ahead with the accelerated test conditions also. That means if I want to simulate 10 years life in 3 months or maybe in 2 months, that is also possible. We don't have to wait for the 10 years. So acceleration test is also important for us. However, whenever we go for accelerated test, we need to think about that it should not change a wear domain. It should not jump from ultra mild wear to the severe or very severe wear. We need to keep that in our mind. If that remains in the same domain, then there's no problem as such. But the wear domain completely changes, then it is not really giving a scenario, similar scenario. It is changing the mechanism. So that should be avoided. That's why when we say that wear testing, we need to really think carefully. Whatever we are doing, is it really correct or not? Another thing is that it can provide us a number of reference data which will be required for the machine learning algorithms. That means we can really generate a number of data on a simple machine which is less time consuming and lesser costly, and we can generate a number of data on this kind of test setup which we are going to describe in the present lecture. However, what is to be done? We say we need to choose a test configuration which should resemble genuine scenario. It should not happen that I can choose any load, any speed, any configuration. I say, "Yeah, this material is good." No, we need to simulate same shape, same composition, same environment. That is very important, and that's why we say that we really require a controlled parameter. That's why we require this kind of setup. So we want to recreate predominant wear mechanism. As I said earlier, that wear mechanism should be more or less same. We should not change this from one domain to another domain. And then whatever we do, it should really align the real world scenario. And for that purpose, we require little more detailing. How do we do that? We say basically we require a tribometer, the tribo interface, which consists of the two parts. That means I want to test one material, we need to have another material against which it we need to perform, or we need to test the performance of the first material. So both the parts are really required, and then they both should closely resemble the real world scenario. Whatever we want real interface, that should simulate the same environment, and then it should have a material composition as well as a microstructure. This is very important. If microstructure changes, particularly when we are talking of the fault detection, we are not talking of the failure detection. If the microstructure has to be there, even then they need to match whatever the we want in a real scenario. And for that purpose, we really require a shape to be same. Like if it is general bearing, the rolling bearing, it is seal, whichever component we want to test, the shape of the component should come, and maybe that we need to make samples according to the that shape. So that's why we say the shape of the component surface, and even suppose after wear out, how the shape will change. Is it really replicating the same shape which happens in a real situation? So that's why we say it should mirror condition seen in practical application. So this is a very important for us. Not only this, we need to keep the rubbing configuration, or maybe right contact ratio. Even the contact patch also should be more or less same. It should not drastically change. It should not happen that, and when we are testing, contact patch is almost negligible compared to practical situation, or it is very big compared to the practical situation. That should not happen. If it is happening, then appropriate model or a scaling factor has to be utilized. If the scaling factors are not proper, then we will not be getting good results. So that's why we say maintaining accurate contact pressure, replicating movement pattern, something like sliding or a reciprocation or variability in velocity, whatever we say, that should be there. Even the environment, even the operating temperature, humidity, and then if there are some sort of corrosive media, or maybe some sort of acidic situation, that also should be present there. And then we say that if possible, however, it is very difficult to figure out the relationship between the frictional energy dissipation, wear and temperature rise. That means we need to know what is the really relation between how much friction is generating heat and how the heat is getting dissipated, and corresponding to that wear is happening. Even though it is very difficult, but if it is there, then it will really give us a perfect situation or perfect simulation condition, and we should test those things on a tribometer. Now, we know that there are many wear setups available, and then one of the publication, SLA publication is there, which provides the results. We say that it has a more than 200. It has described the more than 200 wear testing machines. Again, I'm using the word here, wear testing machine, and if you see here, they are also mentioning about the friction. That means they are measuring the friction, but the title is a wear testing machine. Now they have a given different kind of geometry. That's what we call a 4-ball tester. Then they have a cross cylinder to replicate the geometry. Then they have pin on a flat, particularly, and then we have a multiple contact pin on the flat, flat on flat, rotating pin on the disc, pin on the rotating disc. So this is one of the very common available in most of the academic institutions, and we can really perform number of experiments on that. This is a one thing, and we can think about the disk on disk also is very easily available configuration. So there are number of tribometers, and as I say, this publication itself is describing something like 200 setups which are available in literature. So whichever setup is really closely matching the results, whatever we want to simulate, we can use that kind of setup. Or we have also setup available, commercial setups are available in the market. We can buy and then can simulate around maybe 15 to 20 condition on that tribometer itself. So those things are possible. I'll just describe few things which are important for us. We say whenever we are choosing any setup, or whenever we are making any setup, there are the testing parameter we need to keep in our mind. How much load range we are applying? Is it a 5 Newton to 5000 Newton, something like that? Or are we having some sort of control on the temperature? Are we able to really control the 40 degree? Are we able to maintain, or 70 degree? Are we able to maintain a 70 degree? Do we have a supposed heating chamber or cooling chamber? Are we able to maintain the temperature, the contact points also? So that's as important, and then this will really help us to monitor the wear rate properly. Another one comes to the sliding condition. We have a sliding velocity, then there are some sort of a number of cycles. This can be reciprocating motion also, whether it is in wet condition or dry condition, that also important to keep in mind. And variable shape and size which can be made, and maybe we can use for the on a machine with the proper fixtures. So those are important. And whenever we are doing a wear testing, or we need to keep that in standards in our mind, because there are a number of standards, ISO standards available. They specify if you're doing this test, you go with this standards. They also specify the specimen. They specify the operating speed. They specify operating the load also. So those things are really important to really go through. And when we are trying to compare different lubricant, different materials, so that is where we need to really go with the standards, so that it results of one lab can be compared with the results of other lab if we are following the standards. So we have ASME standards, we have ASTM standards, we have a German Indian standards also, Japanese standards, Society of Automotive Engineering Engineers standards, similarly IEC, GB and IP standards. So these are the methods available or standards available. Whenever we go for testing, we should follow this kind of test. Now let me show me a very common thing, that is what we call a pin on disc machine, and sometimes people use a pod tribometer. Now what is in this case particularly, we are applying a load which is under control. We are making a pin, this is a pin over here, and this is a pin holder, and then pin goes into holder, and holder really allows to fix it properly, so that pin doesn't rotate, or if there's a need, then pin rotates at the desirable speed. And then we are able to see that sliding direction and sliding track. Here the velocity is more or less constant, while we have a possibility of going with a spiral track also, the where velocity can be changed from maximum to minimum, minimum to maximum. Those things are also possible when we are going further this kind of tribometer. So why we want a tribometer this kind? We say that is basically the pin on disc testing is favored due to the cost effectiveness, as I say, the low cost in this case, and it gives a quicker results also. And then it can evaluate the different kind of material solution which we are giving, a different kind of lubricant which we are giving, compared to the full scale machines. However, it is having some limitations, but it can really give us some sort of indication whether which kind of lubricants are superior, which kind of materials are superior. So if there are 50 materials, and then we want to really chalk down only 3 to 4, or we want to select initially 3 to 4 for the rigorous testing, that's possible on this machine. Otherwise, if you choose a all 50 material, go for the rigorous testing, it will not be really the cost economic. So if you choose top 3 material, top 4 material, after testing here in this kind of setup, and we say if we have a 50 material, want to test it, and then we want to rate it. So relative ranking can be given easy way on using this kind of tribometer. So what we say, the what is the purpose to evaluate the friction? Again, even we are using the word we are testing, but we are also evaluating friction, but we are giving more weightage to the wear. So evaluate friction and wear performance during the sliding process. That's the purpose. What are the variables? We can vary the velocity, we can vary the temperature, we can vary the load and lubricant pressure, duration, time duration. I can fix the 60 minutes, 90 minutes, 1 hour. Of course, sometime we can also play with the friction. That means we can apply a desirable torque on the interface and see how the wear is happening. That means we have already decided friction, and then we want to see the performance on that. And then this kind of a setup follows ASTM standards, and this standards or DIN standards, they are already available and being utilized in this case. The question comes, if already somebody has done this kind of test in a lab, do I need to repeat? That means what is the question coming, that whether do I believe published wear coefficient? Somewhat my feeling is that no, reason being whatever the published data, they remain doubtful to some extent. And then this kind of test setup, particularly when we are working with a different lubricant and different material pairs, that need to be at least maybe say few materials should be tested to look at the trend. If those materials are showing the same trend what are the published data, then we can believe in published data. Otherwise we really need to test in our own environment, because there are too many variables, and published data generally are having only some variables, not all the variables. Now in our lab, suppose there are some different variable, naturally results will be different, and results can be even 10 times different also. So better we need to compare, and we will show you there are some results in what we have done experiments in the lab, and I'm going to demonstrate those results also. And in previous lecture, as I mentioned, that whether we go with a wear weight loss or volume loss. So I generally prefer to go with the volume loss, even though this kind of pins weight, we say the initial weight and final weight, and weight difference is measured, and that because of the weight difference, we can find out, divide by the density, we can find out the volume, but that is a base coming from a relation. However, if then there are good formulation or formulas available to estimate where volume directly from a dimension, I prefer compared to the weight, because the weight, as I say, some few polymers have some sort of water content, and few polymers few materials may get oxidized after dismounting from a machine, then the weight will change. So that is very important for us to really keep in our mind, because one is interface and other if we are able to really find out the volume geometry, xy coordinate, then we can calculate the volume, and this is always a preferable compared to the weight. However, if it is not, then will go with the weight, because we are going to go hard only relative ranking. So this is what we say. I prefer to go for the cube in the weight loss compared to the compared to the weight loss, we will prefer the volume loss, and then we can compare materials, even though having a different densities, because density plays important role as such in this case. And then however the challenge comes, major challenge comes, because the worn out area exhibit really high irregularities, asymmetry in a shape. That means we need to know how to really find out the geometry, either in situ or maybe say post processing. If it is done, then it is a preferable method for the weight testing. Just to illustrate what I said, I'm just giving one example. But we say to find out the best material for dry journal bearing, that means we are not going to lubricate it. For the dry condition, how the material will behave against the shaft material, that is something like a AISI 1040 steel. So what we do in this situation, we take this as a steel is a hard material and a costly material. We make a disc of AI SI 1040 steel, while pin material will be made of the bearing material. Like we have bearing A material A, B, C, D, E. So we have 5 materials, and we want to really test those materials against the steel shaft, and the steel shaft is a AISI 1040 material. So we can do pin on disk machine, this kind of thing, and I'm showing experimental results directly here. And then it has been shown that material, of course, they have not followed the Taguchi method, they have not followed the orthogonal array. So some results are there, still we can dig out some information which is relevant to us. Now in this case, we are seeing the A material 3 times has been tested, 2 and then the B has been tested twice, C once, D once, and E once. And then what they have done a testing at the different speeds, different contact force, and different duration. Like 3 materials on the 3 tests for the A material, they have tested for 30 rpm and 60 rpm and 100 newton and 200 newton. Time duration is 350 minutes, 100 minutes, and 60 minutes. Coming to the material B, they have tested again 2 rpm, 330 rpm, 60 rpm. Of course, load has been kept constant, same, and the time duration has been kept a constant. Now coming to the C material, they have tested for the RPM 60, load 100 Newton, and then duration is 480. Coming to E, they have reduced the load to the 100 Newton, and then test also duration is 240. So they have a different tests. So in this situation, I have seen sometimes students, they feel, oh, they have to look at only the how much wear has occurred. So they look at only in wear scar. So wherever they find the wear scar is the minimum, that means the best of material. So here it has been shown that the minimum wear scar is something like 8.81. This doesn't mean that it is the best material. So if it is really required, we need to figure out using some sort of equation. Here again we require a model. As I said that now we don't have any generalized model, we don't have well established model other than Archer or Rabinovics model available, but we try to do a relative ranking. Again, we don't go with the absolute value, we don't build in the absolute manner, we are trying to compare in a relative manner. So again here we will be using some sort of, because dry case, again we can go have the Rabinovics equation or Archer equation. Here we are not saying the which mechanism is going to work. We are saying only that whether wear loss is a more or lesser. If wear loss is lesser, I'll prefer. I know very well that wear loss will be low, but when the coefficient, wear coefficient is a lesser, or maybe minimum among all material. So how do we calculate the wear volume? Generally, there are formulation available, and this is a pin geometry. They make it, and they give at the bottom radius r. You can see here r, and this is a wear scar d in the situation. Now this is a situation, and this wear scar has been mentioned here. So material A 3 wear scar, material B 2 wear scar, and CDE material scar has also been given. This is shown in a greater geometry. We can drive this relation. However, there is assumption. There is assumption is that the disc doesn't wear out at all. That means whatever has been shown over here, this doesn't work. In actual case, there is a possibility that this also gets some sort of wear out. If it is, then we need to change the material, or then we need to account both the materials. Then we need to calculate. However, in this situation or this example, we are assuming this is not wearing out. It's only the pin. Pin is a softer material compared to the harder material, having lesser geometry, and then it will wear out faster. So one is that no damage to disc. Another thing is that wear is planar. That means if it is happening in this manner, if I go when perpendicular arrange the planar, it's showing a plain flat surface. It's not that having irregular surface at the bottom. So that means a roughness has been neglected in the case. So this is assumption for us. So however, if you want to break this assumption, want to go for a more realistic situation, we say ideally surface should be measured using XY stylus profile devices, something like that, or which we have already covered in our lecture, earlier lecture 2. And then subsequently we need to find out the data which can be converted to the digital format to enable subsequent computational analysis. That means we need to require a computer algorithm or computational some sort of libraries which can really be utilized for this purpose. So this is important to keep in mind. However, for present case, I'm just showing you the picture of the one of the tribometer, particularly pin on disc. You can see there is a load cell, and the load cell generally gives a frictional data to us. And the date where it has been applied, and that will be variable. We can increase, we can decrease with. There is a pin holder. The way mentioned, I have mentioned a pin holder. There is a pin which generally we have generally the devices. We can make a pin easy way, but however we know that whatever we make, roughness of the pin cannot be very good or cannot be controlled at the nanometer level. So that will be a problem for us. There's a disk, it can be, and then fixed properly so that there should not be extra vibration. It can rotate only. However, in this case rotational mechanism has been given over here, and there is a speed controller. That means I can operate a 60 rpm, 50 rpm, 30 rpm, 100 rpm. I can do this kind of work with this kind test setup. Wear volume, generally as we say, the wear volume, if I using the Rabinowitz equation or Archer equation, I can equate this manner, and this is been given as a wear volume from previous slide. When you compare, and then there are too many variables, of course d, which we can measure hardness. We know it has been given here for each material. For material A, hardness has been given 225. For material B, hardness is being given 30. C, it has been given 50, and D 70, and E 100. So again, from hardness point of view, somebody say, oh, harder the material is the best material, so 225 will give them the best results. That's a possibility. We can, somebody can conclude. However, it always will be preferable to compare the value of the K. So we are trying to make a similar equation for every case, and the load can be given as the input, sliding distance, and then the radius which we and then has been measured, or maybe the pin radius has been given to us, hardness has been given, and wear scar has been also described. In this case, wear scar is d value has been also described. So if you calculate k value using this relation, so we are finding the first thing, k value is a lesser than 1, that's a good, but the highest value is coming for the C case, particularly where scar is a 16.01, while minimum is coming somewhere 0.021, which is for the where scar 12.63. So this is a different material, and then if you can compare this the fourth and fifth the test, that gives a very good results compared to any other. That means the material B will be preferable. And however, one more thing comes into the mind, that even though results of the B are preferable, it has a lowest hardness, and then compared to A, and then A has also one of the case a very high and the coefficient, wear coefficient. So this need to be tested again, and we cannot just believe. However, this example has been shown to exemplify how the pin on disk calculation can be done and can be utilized for our purpose. So it is not just to choose the best material as such, but just to demonstrate how things work. Similarly, there is another tribometer. What we use the word the block on disk, and then this is one of the geometry has been shown. I can replicate the sliding bearing geometry. I can duplicate in this case, and if I go ahead with some other ratio, even I can try to simulate the gear pair. I can do it. I need to really go ahead with that kind of curvature or maybe dimensions and get the results. Of course, in this case, lubricated or unlubricated, I can do both. If I remove the lubricant, I can then the completely remove the lubricant from this, it will be dry case. However, in this case, you can see here that because of the rotation, oil layer is going up and getting at the interface. So maybe we can say it can be starved lubricant. It's not a fully lubricant. We are not pouring the lubricant from a top. So we are trying to figure out. And of course, there are the driving motors holder, and the disc also has been given. And then here the block can be done a different manner. Here it is, has been made a cubic manner, 12 by 12 by 12. However, it can be changed the way we require. Load can be applied as per the requirement. Now this is the description has been given. We see the consistence of the block specimen is 12 by 12 by 12. However, it can be changed depending on the requirement, and the applied load has a huge range. A big range is something like a 1 to 10,000 newton. The speed range is also very high. We say the 60 rpm to 3600 rpm. And then this can be utilized to simulate the gear pairs. They can be simulated to the tires, bearings, camshaft, pulleys. So this is a very good setup as such. And then we can follow ASTM standards that has been listed many standards on this. We can follow. Of course, some more detail has been given. Also, the Pharex website is been given here, and what we have in the lab is a DuCom. There is a lot of symmetry, or maybe say similar kind of configuration. So we do testing in our lab based on this setup. We have a one more setup what we call as a 4-ball tester, and then 4-ball tester has a number of advantages. What we do here, there are 3 balls at the bottom and 1 ball on the top, and top ball really rotates and bottom ball remain stationary, and that is where we can really test oil, lubricant, whichever particularly even we can use a grease also. So the purpose is to test grease, oil property, and how do we test to figure out whether the friction and wear is increasing, decreasing, intermediate playing in between. So that can be done. That means we can test wear, we can test also friction or performance. Here the preferable, whatever the standard has been given, that the damage these balls are available in the market. That means the ball specimens are already available. Reason being, we are not testing the ball material, we are testing only the lubricant on this purpose. So for lubricant purpose, I believe the football tester is one of the best equipment available and low cost. It also operates at the low RPM, the 1200 RPM, and then there is a fixture and 1.5 kilowatt AC motor. If generally don't require a high power motor compared to this one. Particularly, we do have this in our lab. So in this situation, particularly when we do, we get a scars on the bottom balls which are stationary. We measure their scar diameter and then we do averaging. That means it is very helpful to us to do averaging in 3 balls and come up with the right results. As I say that for ball tester, FPT, there are a number of other setup can be done. This standard is for basically for EP test. What we EP is stand for extreme pressure test, that can be done. And then if I follow IP239, we can go ahead with a lubricant test for the EP extreme pressure as well as the anti-wear additives test also. So these are the possibilities, and then there is a DIN standard which is used for the wear test in the situation. So this is possible, and then as I will say that the bottom balls they get scars. Now mostly they get a circular thing, so vertical and horizontal leading will be same, but if there is a possibility of misalignment or sub arrangement, then value may change to some extent. So this is a setup has been shown here. You can see here is stationary balls, the bottom we are putting a lubricant in this, and then whatever the level has been specified by standard, we go ahead with that, and after that we go ahead with incremental load situation and then see what is really performance against the EP additives, and what is really the welding load, at which load welding will occur. That will be upper limit for the EP additives. Beyond that we cannot operate, or maybe we need to take some sort of factor of safety, so we need to operate the lesser than that load. So that's what we can go ahead with the testing of the EP additives. While coming to the wear, what we do the similar kind of thing, and then we rotate upper ball, keeping a fix the bottom 3 balls fixed. We can really change the temperature, load and speed, and we measure the on the wear scar. Now we can use a optical profilometer, or maybe say microscope also. We can use SCM also, however that will be difficult, so we generally go with a optical microscope in this situation. And we also have some sort of torque reading, so we can analyze the friction, what will be the friction thing. So what we say in this situation, output of the wear test are the frictional torque and the wear scar. If I know the frictional torque, I can find out, I can drive the coefficient of friction from this purpose, from this relation. How do we drive the relation? I just given an example over here. We say we assume that where scar has a radius, and I'm assuming it is a circular radius r, and then we know that the top this layer has been removed from a surface. This top layer has been removed from a surface which has a depth h. So how do we measure this h? We say that we know the triangle AB is being given as a, and h is the depth of the scar from a top, and r minus h will be AB. Coming to the BC, we already are measuring the radius, the scar radius. Then comes AC, AC is already radius. So we can really develop this relation, r square is equal to r minus h square plus r square. Very simple. After simplification, we can calculate what will be the h. So this is important aspect. If I know the scar radius, I can find out the h value. And once I have h, I have to drive what will be the wear volume in this situation, which we are will be giving in the next slide, how to find out the wear volume. However, I have written over here the values. Coming to the horizontal and the vertical direction, as I say, the radius are more or less same. We take average of that if there is a micron change here and there. While coming to the wear scar diameter, in this situation again we have 3 balls, so averaging is much easier. So this is a reliable result from that point of view. Now coming to the torque, we really required what will be the frictional radius. So we develop a relation, equilateral triangle, and then we find out this and then the frictional radius is the 50% of this 0.5776 360, and d is the diameter of the ball in this situation, and ball diameter is already been defined by the standards. So once I know the diameter, I can figure out what will be the frictional radius, and I know the frictional radius, I can find out the torque. So this has been given in next slide. You can see here the coefficient of friction. This is a coefficient frictional torque divided by the frictional radius, and here N has been given as a normal load. Generally we go with a W, but here in this case situation it can be replaced with a W, but for time being we are not using N somewhere else, so I can really write for the load on the ball as such in the situation. Now this is where we have already frictional radius, which we derive from a previous relation, and then I can directly further, because the ball diameters are already fixed, we are using the purchased ball diameter, and we verify the radius are the same what has been given. So coefficient of friction is given the relation as a 0.57 into torque, whatever measured torque, that gives a friction to us. Now coming to the wear volume, which I say then will be driving in this slide. Wear volume is basically what this volume on the top, we want to find out what will be the volume in the situation. So how do we do it? R in the situation particularly, which we are scar radius we are measuring, can be given in terms of whatever relation r minus y square, and then if we go ahead with area, eventually there will be pi r square. Now volume will be A into dy. Dy will can be from a top, and then when we integrate, that we are trying to integrate from an r minus h to r minus h to r, and then in directions we are substituting the value, and then we integrate, and after integration this comes as the wear volume as such. So wear volume is depending on h already we know in terms of r, and there is this whichever ball radius, as well as we have a value of wear scar. So based on that we can really calculate what will be the volume as such. So if I go with this, we can really find out the wear volume. Now coming to the question, can I really generalize the wear equation? People have tried a lot, and then sometimes they have use a wear coefficient directly in dimensionless form. Some authors have given in dimensional form. They don't count hardness. They say that hardness can be increased, can be decreased, so it will be the it can be incorporated in the wear coefficient itself. But this wear coefficient is a dimensional, it is not dimensionless. So whenever you go for the dimensional thing, we need to really keep a unit properly, otherwise results will not be favorable. So what we are saying in this situation, wear volume in the particularly still we are measuring it as a proportional to normal load, inversely proportional to hardness. Same wear volume we are calculating in case of the dimensional coefficients. We are saying that we will not be, we will incorporate the hardness itself inside the coefficient, so that it will really give the right results. And there are some papers who are giving the results in the form. This is one paper of 2018 paper, where they have they found that this wear coefficient in square per Newton, and you can see here there is a 10% variation in the third reading, 1.70 10 to minus 8 to 1.9 10 to minus 8. So there is a variation of the 10% results, and they have used the optimal image of the 200 or 2000 micron, the 2 wear scarp, and they measure, you can see here irregularities. If I'm assuming the constant value, and if I'm assuming it's a perfectly smooth, that is itself is a wrong assumption, because we have found wear scars which come out, they are very irregular, and then if you are calculating the wear volume based on that itself will cause a more errors. So wear simulation procedure, we really require some more detailed digitized values, and if we are able to do, or if we are able to use image analysis and then correlate with our algorithm, that will give always a better results. However, to compare what we are comparing, maybe say when we are thinking about the 4-ball tester, and then we are comparing with the block on the disc drivometer, two different things. And of course because we have this equation, and then we want to just see whether whatever the hardness people have given, what you choose your own hardness, doesn't matter. So that's why just we try to compare. You can see here in one sample hardness is 64 HRC, and for on the block on disk case we have used 40 HRC only. Now this is a value because the balls are already available in the market. This value, when we go for the 60 HRC, naturally the disk also will wear out. So we know we want to keep a lower hardness so the disk doesn't wear out so fast. Now naturally again the load applied is slightly on higher side, 116 Newton in case of the 4-ball tester, while 125 Newton in case of the block on the disc. Coming to the sliding distance, we have a kept almost double distance compared to the block on disc tribometer. Now these are the intentional, and then we want to really compare and show that when we compare this kind of thing, we will come up the conclusion the 4-ball tester is always a better compared to the block on disc tribometer. So that's not a because it has inherent problems. However, if I go with this triple values or 4 times value or 5 times value, then results may turn out to be little better, and I want to really justify why I'm doing it and why we are comparing. Now when we see results, you can see here this orange color on the K is block on disk is very high, and again we are not going as such. We know the K has to be lesser than 1, and real says K has to be lesser than 1. However, we are not using the number of units in this, we are just comparing two values as the relative value, no absolute one. So now here you can see here the orange value is even reaching 160 on the particularly for experiment number 1, and K for the ball 1 is almost even the lesser than 10 is something coming around first case 8.51. You can see here is going very high 160 159.95. In second case is the 5.66, and here it is coming 39.99. So it is no as such no correlation. And interesting thing is the third experiment, K for the 4-ball is a 6.44, but K for the block on disk is almost 0. So this is a very different case. Earlier it is showing very high wear rate, and now it is showing almost 0. So the something is wrong in this case. And then coming our fourth experiment, 3.25, again 39.99. Here 5.12, 79, 5.67, 39. You can see here in this case it is a wear is something lesser, here wear is very high. So again whatever the 8 pieces or 9 pieces we have done is the same hardness and then same geometry, it's not varying significantly. So these are the results which we are getting when comparing it. Now question comes, are these results convincing? No, results are not convincing. That means whenever we use equipment, we need to really keep in mind what are the operating condition and what is really the range. Shall I use a hardness which is really comparable when I am comparing two things? Maybe set for on the 4-ball tribometer as well as a block. That means whatever the relation we are using, it doesn't have a linearity. It is a non-linear relation. So this is what we wanted to conclude, that whenever we go for this kind of test, we really need to keep in mind, then only we can go for the machine learning algorithms. Unless we learn this, we will not be able to clean up the data which are available in the literature. Now if we try to go ahead with some sort of a normalization, and we say okay, whatever the value is, see the normalization, and in this case particularly we say that one of the major problem in on the block and disk is a measurement of the wear. That means wear volume is not been measured, it is weight has been measured. That is the resolution is at 0 microgram, 10 microgram, 20 microgram, 30 microgram, 40 microgram. In between I will not be getting value, and 10 microgram itself is a huge volume. In this case that has been shown in this, if there is a variation this much, we are going to get a lot of error, and that has been plotted on this case. You can see the way the fluctuation in results are possible because this itself is an inaccuracy in a block on disk. So whenever we do perform experiment, we need to know what will the inaccuracy in this. So this has been given inaccuracy in a block and disk as such. Now coming to the 4-ball tester, we can really measure even zero point 0.1 micron wire scar diameter. So inaccuracy will come out to be only 40 microcube volume compared to these values. So we are saying that here in the block on disk, whatever we are trying to do, noise level is very high. Signal digging out proper signal is not right. Now incorporating all, can we really do some normalization? That's what he has done. A person who has done experiment, he has done that way, and we find okay that we will be able to incorporate this inaccuracy into the our experimental results, and we try to compare the results, something like whether coming in proper way or not. So this is where the results have been shown, and we are saying that whatever steel ball we have purchased, we found the surface roughness was very good. However, whatever the blocks which we made in a lab or in a workshop, their surface roughness is not very good. Naturally, the surface roughness plays a major role compared to the material, compared to the oil. So first thing always will come the surface roughness. If the surface roughness is proper, then the results will be okay. Second thing, if the surface roughness is very smooth, we will not have a very major problem related to the wear volume in this situation. Reason being, you can see then this figure, the wear rate is going down. That means if we operate instead of the 700 minutes, or maybe the sliding distance 700 meter, we go for the 7000 meter, we will get a naturally better value of the K. Reason being, running in is not a problem as such, and we already have accounted running in period. This is a major issue in a number of experiments. Students or the researchers, they don't count running in period, because we really require, whenever we are using Orchard equation or similar kind of equation, we require steady state behavior, and steady state behavior, before that running in behavior will come. Unless we count that, the results will not be reliable, and this is what we are trying to convey. And of course, you know that this running in behavior was covered in a lecture 3, and I given in this kind of model which is being referred from a literature. So this is important to cover from that. Now there are some other wear test setup also available. We know that this is abrasion wear test available in this situation, in the particularly situation over here, and this also as per the standards. Now we can utilize this further testing of the rubber material, tires, because when tire runs on the abrasive material or like particles, sand, then what will happen to the behavior, that can be tested. And of course, it has been given the test load, RPM, wheel diameter, everything has been defined properly, and if we follow this test, we will be able to get a reliable results as such. One more thing comes about the surface fatigue. Surface fatigue, we have a number of configuration. We have a two roller configuration, we have a 4-ball tester, we can do it, and the rolling element bearing tester, we have plain bearing setups. So these kind of setups can be utilized for the surface fatigue testing, and we can really figure out what will be the behavior of surface fatigue. And last one, maybe this is what I'm just saying, that there is a challenge, there is a major challenge when we talk about the wear. It has a many factors. When we talk even the testing condition, what will be the friction mode? How do we go with the contact configuration? How we go with the stiffness? If even the equipment is not stiff, if equipment is not is a vibrating significantly, I will get a bad results. So that's very important to keep in mind. Another one is a material condition. When we are talking about the material condition, we need to see what are the material properties as such, what are the chemical properties in the situation. When we are coming to the operating situation time with operating conditions, now what time, the way in previous slide I mentioned, if operating time is more, then actually the wear, initially whatever running in wear, that we are able to compensate. If it is not, then there is a problem and we will not be getting a reliable result as such. Similarly, coming to the lubricant, Many times we add the additives, and we have seen the additives initially behave nicely. After that, they start getting agglomerated and settle down. Performance will vary. So again, the time comes into this. We need to really operate that setup for the more number of hours to get a reliable results. Now coming to the contact condition, really we are going with a very good micro hardness, which is when you coming in the contact. If it is not, then there is a problem. So what are the challenges as such? We say that precise quantification is a challenge, reproducibility is a challenge. At least I've seen whatever experiment you do, reproducibility comes in a very big problem as such. And then if material is getting transferred from one surface to other surface, then what will happen? And that is not treated as a wear, but material gets transferred. So what will happen? How do we analyze that? Another thing is that many times when we take a surface and for SCM and we get a slot the next day or maybe after 4 days, quite possible there will be oxide layer on the material. How do we separate that? And how do we really analyze that? That's an important aspect. And then most of the time in literature they don't provide a detailed setup description, and then compiling that information from literature is going to be a major problem for us. One more thing is that can we go for in situ measurement? In my view, in situ measurement, online wear measurement is the best way to do it. We have destructive testing, we have a non-destructive techniques, and there are enough literature, and I don't want to go in detail, but inline where measurement will be always a preferable compared to the post processing and analyzing later. And then we know that particularly when we are going to talk about artificial intelligence or machine learning, we will be going with the inline measurement instead of going for the post processing. And then if you are more interested to know about the destructive testing and entity technique, one of my courses is already available on YouTube. If you can see the lecture 16 to lecture 21, these techniques have been described as a visual inspection, ultrasonic testing, radiography testing, magnetic particle, eddy current testing, thermographic, liquid penetration, acoustic, strain DIC testing. Stress strain DIC testing is what now the upcoming, and then we can have a many more testing related to this, and that can be done. Even that once we have a complete knowledge, we can figure out how to choose appropriate test for our work. That's also possible. With this I say thank you for attention for attending this lecture. Thank you.